Hello. Suppose that a bungee jumper company hires you. You are given the task of predicting the velocity of a jumper. As a function of time during the free fall part of the jump, this information will be used as a part of a larger analysis to determine the length and required strength of the bungee cord for jumpers of different mass. You know from your studies of physics that the acceleration should be equal to the ratio of the force to the mass, Newton's second law. Based on this insight and your knowledge of physics and fluid mechanics, you develop the following mechanical model for the rate of change of velocity with respect to time. This is the equations for this situation. Now we will discuss about a simple mathematical model. A simple mathematical model can be broadly defined as a formation or equation that expresses the essential features of a physical system or process in mathematical terms. In a very general sense, it can be represented as a functional relations of the form. The dependent variable is equal to function of independent variable and parameters and forcing functions. The actual mathematical representation can range from a simple algebraic relationship to a large complicated sets of differential equations. For example, on the basis of his observation, Newton formulated his second law of motion, which states that the rate of change of momentum of a body is equal to the resultant force acting on it. The mathematical representation or model of the second law is a well-known equation. F is equal to ma. F is equal to ma, where F is the net force acting on the body and m is the mass of the object and a is its acceleration. The second law can be recast into the format by merely dividing both sides by m. A is equal to F by m. Because of its simple algebraic form of the solution was obtained easily. However, other mathematical models of physical phenomena may be much more complex and either cannot be solved exactly or require more sophisticated mathematical techniques than simple algebra for their solution. To illustrate a more complex model of this kind, Newton's second law can be used to determine the terminal velocity of a freely falling body near Earth's surface. Our falling body will be a bungee jumper. For this case, a model can be derived from by expressing the acceleration as the time rate of change of velocity dv by dt is equal to F by m. Next, we will express the net force in terms of measurable variable and parameters for a body falling with the vicinity of the earth, and the net force is composed of two opposing forces: the downward pull of gravity Fd, and there is the downward pull of gravity Fd and the upward force of air resistance Fv. F is equal to Fd plus Fv, the net force. If force in the downward direction is assigned a positive sign, the second law can be used to formulate the force due to gravity as Fd is equal to mg. It is the force due to gravity, where g is the acceleration due to gravity. Air resistance can be formulated in a variety of ways. Knowledge from the science of fluid mechanics suggests that a good first approximation would be assumed that it's proportional to the square of the velocity. But there is a constant CD. CD is a proportionality constant called the lumped drag coefficient. Thus, the greater the fall velocity, the greater the upward force due to air resistance. The parameter CD accounts for properties of the falling object, such as shape or surface roughness, that affects air resistance. For the present case, CD might be a function of the type of clothing or the orientation used by the jumper during free fall. The net force is the difference between downward and upward force. Therefore, equation can be combined to get mass into dv by dt. This is derived from here, where force is equal to mass into dv by dt is equal to we will divide both by m. After dividing, we get the last equation. dv by dt is equal to g minus cd by m v square. Equation is a model that relates the acceleration of a falling object to the force acting on it. It is a differential equation because it is written in terms of the differential rate of change dv by dt of variable that we are interested in predicting. However, in contrast to the solution of Newton's second law, for the velocity of the jumper cannot be obtained using simple algebraic manipulation. Rather, more advanced techniques as those of calculus must be applied to obtain an exact or analytic solution. For example, if the jumper is initially at rest, calculus can be used to solve the equation. So we should integrate this equation with respect to v, velocity. After integration, we get the equation v of t is equal to root of gm by cd into tan h of root of g into cd by m into t. This is the last equation. So we can this is the last calculus equation. We should note that in this general form, this v of t is a dependent variable and the t here is an independent variable. Time is an independent variable and cd and m are parameters and g is the forcing function. Every equation that we derive should have dependent variable and it should be a function of independent variable, parameter and forcing function.